Okay, let's get started with this topic. Sync versus async, or synchronous versus asynchronous. So sync versus async. Make it this get bigger. Make it bigger. Where is the size? Are you kidding me? Wow. Color. Oh, let's see this one. Alright. So synchronous is very simple. Most of the code is synchronous. So for example, any code you write is synchronous by default. Synchronous just means that things are executed in the order, one after the other, unless you have a condition of course, if you have a loop, that will break that order, but otherwise it would be C control. And it's pretty simple way to order things. So for example, if you have a recipe of a cake, you would have step 1 buy eggs, step 2 crack the eggs, and so on and so forth. So pretty simple to understand, pretty simple to follow. When we do async, we want to break this particular model, and the main reason we want to do that is because there are some steps that may take a while, and in a synchronous model, everything is blocking. Right? So the important concept is that things are blocking. Blocking means that in order to go to the next step, you have to finish the step before. So if the current step is taking a while, for example, because it's downloading a file or it's sleeping, it has to wait for a particular time, then the next action will not be taken. And in fact, nothing will be done. The CPU will just be waiting for that step to finish. And that introduces us to another idea, is that when we say async, we do not mean parallel, right? So let's make the distinction here: concurrent versus parallel. So concurrent is usually the same as async. So when you do when you do things concurrently, the method you're going to use is asynchronous programming. And concurrently is doing things like, well, basically normally you do things concurrently. It's like multitasking. If you were to make a cake and one step is to wait for the cake to bake, like it would take an hour and a half, for example, for the cake to bake, it's not like you're going to wait in front of your oven for an hour and a half, right? So if you have other things to do, you will most likely go on to your life and then do the other stuff. So this thing is that you're doing things concurrently means that you are able to intertwine different tasks, different steps together. So the main task would be bake a cake, but you also may want to watch TV or go shopping. And in the synchronous model, you will have to wait an hour and a half in front of the oven before you go play a game or something else. Okay. So in a concurrent model, you would notice that step takes an hour, and actually you can do something else in the meantime. And it's not the same as parallel, because parallel basically is the model where you have several people working on the same task in parallel. So you can think that parallel usually means multiple processing units, so multiple CPUs or multiple cores. But concurrent doesn't mean that. You can do concurrent with multiple threads, but you actually could do concurrent with only one worker. So you can process things concurrently while you're obviously one single person. But if you do things in parallel, then you need a team, right? So that's maybe interesting to notice. So I'm going to put this away for a moment. But blocking is important, right? Blocking is the main difference between why you would want to do things asynchronously versus things synchronously. And there's a cost, of course, to do things asynchronously. If you sum all the things together, it would probably take a little bit more time, and also it's harder to program. So the easiest model is synchronous, right? So you kind of have to think whether you would benefit from switching to an async mode before you just jump into it. All right. So how things are done asynchronously? Actually, there are several ways to do things in async mode. The very primitive and historical way is to do with the event loop. Right. Let's say event loop. That's the model Windows. Well, many other systems are like that, but Windows is a pretty famous one. Windows 1 already had an event loop. So the idea of Windows was that you could run applications and you could switch from one application to another. Even though at the time, of course, we didn't have a CPU that have multiple cores or multiple CPUs. Maybe they existed, but they were extremely rare. So Windows were targeting regular CPUs, and that would mean one CPU, one core. And yet they want to emulate the multitasking and running multiple applications at the same time. So this is really what Async is about, right? So you will be able to start working, for example, on Notepad, and then switch to another one, calculator or something like that. And for that to work, these applications needed to be written in a very particular way, right? So this is not the same as threading and processing, multi-process. So we can also put it here, process and threading. This, when you have mythical processes, so now most operating systems are using multitasking, and they use preemptive multitasking. Multitasking or multiprocessing? Let's say multitasking. So the preemptive is important part. It means that you write the application normally without any particular attention to having it running in parallel. And then when you run in the operating system, we'll be able to actually simulate the same thing, simulate having these guys run next to each other. So it's simulation of parallel, because since you only have one core or one CPU, there's no way for you to run things really in parallel, right? It actually means running concurrently. So one guy will run for a particular period of time, and then the operating system will say, okay, enough of that. I'm going to suspend you. I'm going to preempt you, and then I'm going to put you on the side and execute something else. And then when that thing is execute for a while, it will also, the operating system will come back and say, okay, this is enough for you. Let's go back to the first one. And this dance of switching between applications, processes, is done mostly without you taking, without you having any interaction with it. It's automatic and it's done by operating system. And it's done in a way that you can't, your application cannot say, okay, no, I want to have the entire CPU for myself. Unless you have root privilege and you have a particular kernel access, blah, 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 right? A normal application would not be able to say, okay, I take all the resources and forget about the other guys, right? So that's the preemptive part of multitasking. And Unix is preemptive, Windows is preemptive. Most operating systems now are preemptive, right? But what we are talking about is cooperative multitasking. So we are talking about how we write our own application in a way that it will do multiple tasks concurrently without help from the operating system. And you may ask, why do we even bother? Because the operating system is actually going to do the job for us, right? Even if we write a sleep 2000, and then we also a long sleep for like an hour, and then we write something else. The operating system we notice that the sleep is useless, and it would be using unnecessary resources if the CPU was kept idle for an hour. So the operating system will automatically put our process on the side and start another one, not switch to another one. But the reason why we still want to do this is that we don't control the switching, right? We don't control whether it's going to switch to our own program or switch to another program. So the only way for us to make sure that it switches to something that we have to be doing is either spawn multiple processes, right? So that was a very old way to do things. If you wanted to do things concurrently, well, you wouldn't run multiple processes. You would run basically multiple programs. And the first versions of Python were like that. If you want to have, for example, a web server that handles concurrent connections, then you will run multiple instances of Python. You could have tens or hundreds of Python processes, and each one of these processes is actually taking some resource in the kernel. Right? You at least would have to have an entry in the process table to keep track of these the process state. And scalability is not very high. Right? So if you are talking about a web server only running concurrently because of spawning multiple processes, I think after like a few hundred connections, or maybe a few thousand connections, the machine will be overrun. So the other way to do this is threading. So the difference between processes and threading is lighter. Threading is very similar to process, meaning that you also can control it from your application. In your application, if you want to spawn another process, you would first duplicate yourself. You do something called a fork in Unix, in a Unix fork, which is a system call that duplicates your process. And then when you have a second copy of process running, you will run exec, which basically replaces your process with another executable. So they usually go together, fork, exec. So you can look it up, and that's not super important to know the details. But essentially what I'm trying to say is that what you do in a shell when you launch commands from the command shell, the command shell is basically doing that. When it reads your command, understands like the syntax, and then it would fork another shell, and then exec your binary from that secondary shell. Right. This is a bit expensive, right? So if you have a process that actually wants to also run multiple copies of itself, but in a lighter way, it can use threads. And threads is basically very similar, but you don't have another entry in the process table. So there's only one process when you have multiple threads. And the other thing is that these threads will share the same memory space. So when you have processes and you allocate memory in one process, that memory is not going to be reachable, available to the other process, even if they are copies of the same one. There are ways to communicate between processes. There is multi-process, inter-process communication, IPCs. But it's another topic, and by default it's not happening. Right? The memory is not shared. For threads, it is shared. So this is both a curse and a blessing and a curse. Blessing because you don't have to make any special effort to have one thread read the data from another thread. Right? The curse is that if you do that without paying care, you can have multiple threads reading and writing exactly on the same memory at the same time. and that will lead to memory corruption most of the time. So threading is still a very useful tool, and but we cannot go overboard. We cannot start spawning like hundreds and thousands of threads as well. So they are still they are lighter than processes, but they are not super light. So and switching from one thread to another also takes some time. It's in the microseconds, but it is some noticeable time if you are constantly switching threads. And last thing is that thread is also managed by the operating system. So switching between threads is also something that is preempted by the operating system. So what we learned so far is that we have this massive tool, which is OS preemptive multitasking. And with this, we have this simulation of concurrent behavior without too much effort. Right? So if we use this and we run different apps, then this is the stuff that makes it look like we're able to run multiple apps at the same time. This is if we have one process and we want that process to do multiple things. And we want to take care of the communication, right? So that model, the model of multi-threading, is like the evolution of multi-process. And web servers, they originally were multi-processes, and then they became multi-threaded. Right? So it is quite popular now to say, okay, I know about multi-threaded programming, even though this technique is now pretty old, is at least like 10-15 years. So that doesn't help us too much with like async. Right? We're still like wondering what async is, because all this stuff doesn't require us to do anything that is particular. We can still write synchronous code with all this stuff and not have any problem. So async is when you start being very concerned about your resources, and you want to actually control where your program is going to stop and where the program going to start switching to other tasks and so on and so forth. So you can imagine that async is the same as multitasking, but it's done in your application. It's not done by the OS. So we call it cooperative multitasking, and there's one thing that comes is often is the idea of a green thread. So green thread. So normally this is just by opposition to these OS threads. OS threads are obviously maintained by the operating system, and green threads will be maintained by your application or your library, your language library. So these guys are not really like well, they are threads, but the operating system will not see anything coming from them, right? So if you do a PS, if you do any tool to list the state of your processes, you will not see green threads, because this is an entire application concept. So what is that stuff about, right? So it comes back to this guy, this even loop, right? So if you want to do multiple things, right, and then you have to decide where you want to stop, where you want to suspend your task, right? So let's go back to the example of cooking a cake. So this time you want to cook a cake, but you want to do it asynchronously. So step one, blah blah, crack the eggs. So you look at these guys and you see getting the eggs. Well, we have to go to the store. That may take a while. Best if I even send somebody else. But let's say that I already have my eggs, right? And now I just need to crack them. I need to maybe like whisk them and then add the flour, the sugar, right? So this stuff doesn't really take that much time, right? Especially if I prepare them in advance. So there's no reason for me to expect blocking, right? Because if everything was prepared, these steps will go like smoothly, right? So you write your program normally. So it would be like okay, let's do it in JavaScript. So it would be something like function make cake, and then you will have crack eggs, whisk eggs, add flour, okay, and so on and so forth. So a bunch of these guys, right? And so far nothing is asynchronous. Then there's a part where you go and you say cook, bake, right? And that one, if you need some domain knowledge, right? So just saying bake, this okay, by default there's no way the compiler would know that bake actually takes a while, right? So if you write bake like that, then yeah, sure, it's gonna take like an hour to bake, and then okay, let's see, after bake we say eat cake, right? So the problem here is that eat cake will you make the call to make cake, it would take an hour before we return from that function, because that bake cake here is gonna take a while. Even if you eat the cake super fast, this whole thing is gonna take an hour because it's limited by this guy, right? So we have a sequential function, and one of the step is very long, right? So what do we do, right? So we would like to actually leave the function at bake. So we start the baking, and we want to return right away from that function make cake, so that we can do something else, right? And then when the baking is finished, we want to resume that guy, right? So that's not going to be magical, right? The fact that you want a function to stop and resume, you have to remember that this is not a model that the CPU knows. No, the CPU always executes things in the order. It doesn't know about okay, you have to suspend, you have to call me back. All this stuff is going to be done by you or your library, right? So first thing is we need to isolate to know that this is going to take a while. So we know this function is spatial, right? And that makes this whole thing special, because now this function is not simply entering and then going through the stuff and then exiting. It's a function that you enter, you do something, and then I have to stop. Okay, let's resume later.